Hi, everyone. We worked on a dice recognition project. The team consisted of Bryce, Lily, Ronan, and Sophia. In our presentation, we will start by discussing our dice classification workflow. We will discuss individual components, including Otto's algorithm, thresholding, and connected component labeling. Then we will discuss some of our optimizations and the key results we observed. The goal was to determine the value of multiple die within one image. Our dataset consisted of 80 images with 5 to 7 die in each image. You can see an example on this slide. We fed the input image into Otto's algorithm, then performed thresholding and connected component labeling. This outputted the classifications for that image. The first step was Otto's algorithm, and the goal was to determine a threshold value that maximizes the interclass variance. By doing so, this minimizes the variance within a class, which then ensures that each class consists of similar pixels. The procedure consisted of creating a histogram for all pixels and then choosing an initial threshold value. We then computed the variance that was created between the two classes. Then we repeated this for all possible threshold values and then outputted the threshold value that maximized the variance between the two classes. For thresholding, the goal was simple. It was to binarize the image based on the provided threshold value. So every pixel value that was below the threshold was set to 0, and every pixel value that was above the threshold value was set to 1. You can see an example on the slide.
The goal of connecting components is to label a connected group of white or black pixels. The picture depicts the output of connected components on a binary image where the white clusters are being labeled. We had two separate implementations for connected components on white clusters and black clusters. They're very similar with the exception that connected components for black clusters also store the label of the white class next to it, so we could attribute a black dot to a white dice. This is the data flow for connected components. We first stream in the pixel starting from the upper top left, and then we threshold that pixel. We use that thresholded value to run connected components for white clusters, and then afterwards we run connected components for black clusters. We loop through this process, iterating through the whole image. Afterwards, we use the outputs to determine the number of black dots connected to or connected to a white cluster, and then we use that. We stream out the dice values. The algorithm for connected components checks the upper diagonals on top and left pixels, and then using that value determines whether to create a new class label or to assign it to the lowest class label of those pixels. Also, the algorithm can result in a cluster having multiple labels, so we use an equivalency list to merge equivalent classes. Because we cannot store the whole image in memory, we use a line buffer to store the thresholded values and the class labels of a pixel. The line buffer has to be big enough so that it stores the upper diagonals of the pixel. And the benefit of a line buffer is that when we're checking a new pixel, we can just use inexpensive shift operations to update the line buffer. We use the equivalency list to find the unique black clusters, and then we use the size of a cluster to filter out noise and actual black dots. And then we get the label of the cluster that's next to this white cluster that's next to this black dot, and we add 1 to the dice value of that white cluster. And then afterwards, we stream out the dice values of the white cluster. This works pretty well, except when the image resolution is poor and black dots are connected together, this can hinder the accuracy.
So now we're going to talk about alternate design optimizations that we made to help increase the speed up. So we first use seamed algorithm to decrease the image size. So if a row or column is all black, we cut down that row and column from the image. And so we could decrease the number of pixels from a 410 by 410 image to a 210 by 210 image. This decreases the memory access from the CPU to the FPGA board. As well, we remove Otto's algorithm. So we selected a constant threshold values of 107 based on the median thresholds of all the images that we have. This could be heuristically correct usually. And this cuts the number of streams into the kernel by a factor of 2, since we now don't need to stream into the kernel for the first time for the Otto algorithm. So we only do it for the regular connected component part. We also reduced the number of bit lengths of array indices and reduced the array size. And we inserted unrolling pragmas to duplicate hardware for critical loops.
So according to, after our optimizations, we can see that they had a pretty substantial effect. So in COSIM, after our CSynth, we were able to check the reports and see that our maximum latency decreased by an order of 100 approximately. So we started with 139 million cycles, and this decreased to 3,700,000. So this decreases our execution time by a substantial amount. We also reduced the number of lookup tables. In our alternate design, we're sitting at a comfortable 7,921, which is very far under the Z board's 55,000. We were running into issues with the lookup table count before we made some of the previous optimizations, or when we were working with various optimizations. It was a problem because to keep the entire image in the FPGA, it's very large. The number of flip-flops also sits under that value. Now we're going to show a quick demonstration of what our FPGA can do. So we're going to classify this. Wow, that totally, okay. Let's try this again. Now we're going to show a quick demonstration of what the FPGA can do. So we're going to classify this image here, which has a 1, a 4, a 3, a 5, and a 3. It's a 410 by 410 pixel grayscale image. So the first thing that we do is we run a pre-processing script, which runs Steam's algorithm as discussed before, which shrinks the image into a 210 by 210 image, which still preserves all of the dice. So we're able to shrink it down to 210 by 210 because it still preserves the dots while getting rid of a lot of the black space. And by shrinking it from 410 by 410 to 210 by 210, essentially cuts the number of pixels we're putting in by 4, which significantly decreases the number of memory accesses that the FPGA has to do. Since we're working with a bandwidth bottlenecked system, the less memory accesses we have to do, the better, which will result in better latency. So here we have the SSH kernel. We've SSH'd into the Z board. And we can see that we've converted that image into a text file, which has all of the hex values representing the different pixels in the image. So each hex value is actually 4 pixels in one hex. So we have like 0C, 09, 07, and 0B. So these are each representative of 8-bit grayscale values, which all get passed in the same packet. So the reason why we do this is because we have a 32-bit input stream into the Z board. So by putting in 4 pixels at a time, we can make maximum use of the bit stream that we're given. So we can see now when we use the Z board, if we type in, 1 second, when we actually run the FPGA, we write make FPGA to classify this 14353 image. And so our host program is running, and we put in, it can tell from our input file name, we have a 1, 4, a 3, a 5, and a 3, and we classify 14353. And we have a 37 millisecond total time. So if we run this again, we can see that the time fluctuates slightly between runs. So after running it again, we can see that it actually decreases to 26 milliseconds. So after testing, we found that our FPGA generally runs between 25 and 35 milliseconds when running the image. It tends to fluctuate based off of varying factors. So that's what our demo looks like. And on different images, sometimes we can get a slightly lower accuracy because the dice can blend together in certain images. But for the most part, we range between like an 80 and 95% accuracy. So thank you for taking interest in our project. If there's any information that you'd like more information on, please check our report.